All right, so welcome everyone to today's webinar. I can see that already a number of people joined us today, so I suggest to wait another minute before we can then start and jump right into the topic of today. All right, so let's start right away. Welcome everyone to our webinar. My name is Magdalena. I am responsible for marketing and sales at DH Electronics. And today you will hear our webinar on how secure embedded solutions for industrial applications can be realized with STM32MP13. I brought two colleagues of mine, which are Andreas Geisreiter, who is the product manager for our 𝗙𝗏 family, and also Johann Neuhauser, who is a software developer and expert for software and cybersecurity as well. So for the rest of the presentation, we will switch off our camera so that you can see the presentation on full screen. And also, please don't hesitate to put your questions into the questions sections. Usually you find a dedicated window, and there you can just ask whatever you want. And in the end of the session, we will answer all your questions. You could also use the chat window, but usually for us, it's a bit easier if you really use the questions section and write down what you want to know afterwards. So today, I think I can give you a short outlook. Today it will be a lot about software topics, but before we dive deeper into that, I will give you a few information about our company, DH Electronics, so that also those of you who have not heard of us will get a short impression of what we're doing. And also Andreas will, of course, talk a bit more about the DH core STM32MP13, which is a solderable SOM, and which we refer to when we are talking about secure embedded solutions platform today. So as mentioned before, I will now switch off my camera so you can then see the screen in full size. And yeah, as promised, just a few words on DH Electronics, because today it's mainly about security topics. So just a short intro. So DH Electronics, for those of you who have not heard of us, we are a medium-sized company located in the very south of Germany. We have more than 25 people working in our engineering teams. And we have three main product families. Today it will be all about our 𝗙 family, which are solderable and pluggable system on modules. Apart from that, we have other standard products such as IoT gateways and HMIs. They are all based on our own SOMs. And what we also do a lot and have done in the past for more than 30 years now is the development of individual embedded solutions for different kind of industries. This can be HMI solutions, controllers, any sort of control or visualization units. And we also offer really customized embedded solutions. And for all of those, our SOMs are, of course, the basis. And today, security is more and more important, and that's why we want to highlight this topic and also want to explain to you what ways and what possibilities you have to make your devices secure, and also what we try to deliver when you buy one of our products. So I think that's all for now. I don't want to spend too much time on presenting our company and products. I think it's important to know that we do not only provide SOMs, but that we also have own products that we have to maintain on our own, that we have to keep safe and secure over time as well, that this lifespan is usually 10 or 15 years. So we really have a high interest to keep our products up to date, especially the BSP and the SOMs, of course. And that's where we want to have a deeper look on today. So I will now hand over to Andreas, who will show you a bit more about the solderable SOM based on STM32MP13 before we will then move on to real hands-on tips of what you can do, especially in the software development, to keep your industrial application secure and up to date over time. So Andreas, it's your turn.
So thank you, Magdalena, for the intro. Maybe some words to myself. So I'm Andreas. I'm working at DH since 15 years now, and in the company I'm responsible for the system on modules. And before we go deeper into the secure boot topics, we would like to give you a rough overview about our solderable DH core STM32MP13 system on module. This module comes in a size at 29 by 29 millimeters and has the following components directly on the SOM. So first of all, the CPU itself, the power management with ST-PMIC, DDR memory, eMMC for storing the Linux image on it, 4 megabyte SPI boot flash for storing the U-boot, single band Wi-Fi Bluetooth solution from Murata, an EEPROM, and a temperature compensated RTC. The hardware of the SOM can be configured to the needs of your project. This means you can choose the size of the DDR memory you need. You can decide if you want to have RTC mounted or not, and so on. And furthermore, our SOMs comes without a standardized pin assignment, so you can really use the full feature set of the MP13 directly on your main board. Because in our case, you're not bound to a standard with our DH core. I will show you 2 standard configurations later, but these are just 2 examples of configurations that can be adapted to your project needs. I would also like to say some words to the soldering technology we are using with our SOM. There are big differences in the solderable SOMs on the market. And in our case, we apply a lot of solder paste to the underside of the SOM during the production. And these pre-tint pads makes it easy and safe to manufacture the SOM. We have been using this technology for over 10 years now, and we and also our customers, our SOM customers, have never had any problems with it. Okay, Magdalena, can you switch to the next slide? This slide shows you This slide shows you an overview about the 2 standard pin configurations for our SOM. One is a headless configuration used on our single board computer, which I will describe in detail later. And the other configuration can be used for HMI applications. As mentioned above, the pin assignment can be customized to the needs of the project. However, to reduce software board support package development costs, I always would recommend starting with one of these 2 standard configurations. Okay, so next slide, please. Yeah, on this slide, I would like to highlight the power management on our SOMs. I think we do something different from our competitors. In our case, we supply the SOM with a single 5-volt supply Then we have the ST-PMIC, which generates all the necessary voltages on the SOM. But the interesting thing is that we also provide some of the outputs of the PMIC directly back to the mainboard. And this means that our customers can use the PMIC outputs to power their own mainboard, almost as if they have done a design-in of the SoC itself. And this brings the following advantages. So reduced costs on the mainboard, because you can save costs of additional buck regulators. Then the power sequencing on the mainboard is done directly by the SOM in that case. And especially if you need low power modes, you can disable dedicated power outputs of the PMIC and switch off also the power supply on the mainboard itself. And this really can reduce the power consumption if you enter suspend to RAM mode. And please note that the power supply of our reference design, our DH-SBC board, is exactly done in that way. Next slide, please. Now we will have a look at the reference design, the DH single board computer based on our DH core STM32MP13 system on module. The most important thing is that this is not just a development board, but this is a real industrial design that can be used directly for a project. The board comes with Raspberry Pi form factor, and in addition to the features of the DH core system on module itself, the board comes with the following features. So we have the Raspberry Pi expansion header on it. We have dual gigabit Ethernet interfaces. We have USB host port. We have a USB device interface via USB Type-C connector. And this interface can also be used to boot the MP13 over USB. We have a USB compatible power supply. We have a trusted platform module on it. We have a boot mode switch, reset power button, cell coin socket for RTC buffering, and a console connection via pin header. As I said, the board is designed for real use in industrial applications. Therefore, we also guarantee the availability of 10+ years, and we also have done a CE certification for this product. Regarding pin configuration, we used this mentioned headless configuration in some of the previous slides, and the power management is exactly done as mentioned in the slide before. So we only have a 5-volt USB power supply here, and the ST-PMIC itself generates all the needed voltages on the board. And so you can really reduce BOM cost of such a design. Next slide, please. So in the next 3 slides, we will focus on the board support package with Linux and the Octo. And the most important point is that we are not using the vendor BSP package from ST, so the so-called OpenST Linux distribution by default. And the reason is simple. We like to be vendor independent to ensure the long-term maintenance, especially. Overall, I have to say that ST does a great job with their Linux package, but for the long-term maintenance, we need also the community. Because today the MP13 is a new product and in focus of ST. There will definitely be the case for the next few years, but our devices on the market, so we have devices on the market for the next 10 up to 20 years based on this product, and definitely ST will focus more on new products in the future. Then we have the problem that the response time for security or bug fixes may be too slow, especially when we consider the new European Cyber Resilience Act. That is why we as DH focus on mainline Linux, because it is not just a single vendor, but the whole community that has been maintaining it for years. And we also benefit in that case from ST's good mainline work, because ST also upstreams as much as possible to mainline Linux, and that work is also part of mainline Linux and not only of the vendor BSP package. So overall with mainline Linux, we benefit from having optimizations, improvements, bug fixes available to everyone. But in order to use mainline Linux, we must upstream the support for our SOM to mainline Linux. But since you cannot upstream the SOM support directly, because a system on module is not an end device, we have to upstream the support for our reference design. With our 𝗏_core system on module, this is a previously introduced 𝗏SBC board. This is what we have done for the MP13 and also for all other system on modules from 𝗏 Electronics, so of course with a different reference design. And this step allows you to use the latest available Linux kernel version with our system on module. But for embedded devices, the normal way is to use the latest long-term support kernel, currently the 6.6. And this is exactly what is part of our Yocto board support package layer. This will also make it easier to maintain. Magdalena, please back. This will also make it easier to maintain the Linux support for your device, because not only 𝗏, but also the whole community will providing the maintenance. And our goal is also to keep the number of patches in our board support package layer as low as possible. Means we try to upstream as much as possible with the goal to remove some patches again with the next long-term support kernel update, because these parts are then already be part of mainline Linux. What we also can do for your project is to upstream the support for your product directly to mainline Linux, and this then makes it much more easier also for you to maintain the Linux system over the time for your specific device. Now, next slide, please. On this slide, I like to highlight our Yocto structure. And by default, we provide a Yocto-based board support package with our SOMs. So now I would like to give you an overview about the layer structure. And the goal is that our customers can reuse as much as possible for their own projects. I have used 3 colors for this diagram. Blue parts means this comes directly from Yocto project. And these parts are more or less maintained by the Yocto community. The interesting parts are now the green parts. This comes from 𝗏 Electronics or DANGS, and is also maintained by these 2 companies. And let's start with this Meta mainline common layer on the left side, this green block, which comes from DANGS and is used to get the sources for the kernel, U-boot, and some other open source components. This layer is hardware independent. This is important here. Then next we have the Meta 𝗏SOM STM BSP layer, which contains the customizations for our SOMs. This layer is maintained by 𝗏 and is independent of the specific end product. It contains only the customizations for our system on module itself. And finally, we have this Meta 𝗏SOM extras layer, which is an example of a project-specific layer. With this layer, you can also test typical packages like, mentioned here, WebKit, Flutter, Qt, and so on. If we now start a project with our 𝗏_core system on module, we have to create a project-specific layer. And this is done as copy from Meta 𝗏SOM extras with all the adjustments for the board and the needed packages. Apart from this, all the other layers mentioned above remain unchanged. And so this has the advantage that the board support package update from th can easily be reused. Yeah, overall, the goal is that our customers really can reuse all the maintained layers from us, and they only have their project-specific layer, which needs to be adjusted to their own project. And this should also make it easy, more or less, to update to a new version from th Electronics, because you only have to be connected to this single layer, more or less, and the rest is directly provided from us. This is the idea. And I also must say that all our SOMs use the same structure, so it is more or less easy to move from one SOM to another. Can we switch to the last software, Linux software slide? Okay, on my last slide, I'd like to give you an overview about the BSP board support package update schedule. Of course, our updates are tied to the Yocto and Linux long-term support releases. So on Linux side, a new LTS kernel is released at the end of each year. With Yocto, we have a new long-term support release every 2 years in Q2. And therefore, we will update our BSP to the latest long-term support kernel release at the beginning of each year, and to the latest LTS Yocto release every 2 years around Q3. In the meantime, it makes sense to stay on the latest LTS releases for both for Yocto and Linux, and only update to the latest available patch set from time to time. But this can be done very easy within each project. So we spoke about Yocto structure and up-to-date Linux system. And now I hand over to my colleague Johan. Hopefully he is available, who will give you an overview about how to secure your device for your specific application. So is Johan there, or does he have connection problems?
Yes, I can give a short update. Johan should join in less than a minute, and in the meantime, I can also connect to our standard Wi-Fi, and then I can use both of my screens as well, and you can see the usual PowerPoint presentation. So just give us 1 more minute. Sometimes we don't have the techniques in our hands. 1 second.
Hello?
Yes, we can hear you, Johan.
Okay, should I share the presentation by myself, or I don't see any presentation? I'm a bit confused, sorry.
Yes, I think Magdalena also reconnects from her desktop PC.
I can share it, but I don't have the rights to share my screen.
Okay, let's wait a second. I think Magdalena will share it again. Yeah, now it looks fine.
Seems good. So, Magdalena, can you please switch to the next slide? Or you finished, Andreas? Yeah.
Yes.
So,
yeah.
Hello, I'm Johan. I'm a software developer at 𝗪 Electronics. And today I tell you something about platform security services especially in terms of the new STM32MP13. Yeah, what the requirements for platform security services? Firstly, we have hardware requirements, and the STM32MP13 has the trust zone extension that's required for the CPU to partition the CPU. It has also a MMU, which supports the memory isolation through the trust zone extensions. And last but not least, we also have the secure boot feature, but most of us know this. These are only supported on the F and C variants of the STM32MP SoCs. Yeah, so the next requirements are my parts. The main requirement is the trusted boot chain, and the trusted boot chain is consists of TFA, the trusted firmware for Cortex-A ARM CPUs, then the T itself. This is the open portable TOS, and finally the Linux with support for OPT and the T-client API. What are common platform security services that could be achieved? The first one is key management, to store keys in trusted environment, and like a smart card or hardware security module. Authentication, to validate that it's really the person or device that I suggest. The next one is secure storage, to store valuable information in a secure context on an unsecure device. Unsecure device means storage device. Yes. The next one is the most important one, or also a very important one. That's the cryptographic services. This are provided through Linux or any other OS which uses the OPT driver and the T-client API to use services from the OPT. The last two, attestation and tamper detection. Yeah. Okay. Then let's start with the block diagram of the STM32MP13. Magdalena, can you please switch over to the next slide? So these are the block diagram of the STM32MP13. The yellow box are the security features which are provided by this SoC. Oh, this is a very long list. And the red ones, these are the main components for providing secure platform security services on this device. The first one I mentioned the slide before was secure boot and trust zone extensions. These are the hardware features. And especially the STM32MP13 has a pre-programmed hardware unique key. This means every SoC this has a unique elliptic curve key, also asynchronous cryptography, to maintain device security. This is special for the MP13. And what's also special is the OTF on the fly DRAM encoding decoding. Is a bit confused, but this means the 𝗵13 supports RAM encryption to store private information that could be extracted by physical manipulation or the disassembly of the device. Yes. The other two components, the one-time programmables are required for the storing the secure boot certificate, and the system RAM is for running, mostly for running the trusted execution environment, as this can not compromised by physical manipulation. Okay, then please next slide. So here's a short overview about secure boot on the STM32MP13. What against more than the MP15 is the ROM code supports up to 8 certificates to sign the images for secure boot. This means if a certificate gets compromised, I can switch to the next one and I revoke the key that was compromised. But yeah, I think the overview is a bit complex. It consists mainly of the key generation, is done with the tools from STM. Then we have to burn the hash table, also the hash of the table of the public keys into the one-time programmables to fix it to this set of keys. Genau, und image encryption is more or less optional. As you could, but you don't must. Genau, und image authentication with the revocation version rollback. The revocation of certificates does work by using a certificate with a higher index, and if the device boots with the certificate of the let's say index 1, all certificates with an index number lower than this, in this case only the index number 0, are revoked and can never be booted on this device. So if this device was booted with the new key, the old one with the lower index is locked out. And the last one would be the optional image encryption. The image encryption means this is the first stage bootloader. This is trusted firmware A in this case. Or in the basic boot, this would be the U-boot SPL. Genau. Yeah, and secure boot is the foundation for the secure platform security services. As if anyone could exchange one of my components in the boot chain, he can take control over the whole system. That's why it's the main foundation for this services. Next slide, please. So the security building blocks for platform security service are mostly the hardware extension IAM Trust Zone. And on top this, the first, after the ROM code initializes the hardware, then it loads the trusted firmware A, TFA in short. This tiny part of this boot chain prepares the normal world and the secure world. To this, I come later to this. And it also enforces the chain of trust with the TFA called trusted board boot, but this is the same as secure boot in general. Just only another name, another implementation, but it ensures that the chain of trust is valid. And last but not least, it also handles secure firmware updates. This means if the Linux or the update download client gets a new update file, this is stored on the boot partition or anywhere, And on the next start, TFA checks if there is a new update on the storage. Then it executes the update and handles it by itself. Yeah. All stages after TFA doesn't need to handle anything of updates. The reason why it is implemented in TFA is as TFA is more or less stable and minimal enough to keep it on the device, as this is the first stage bootloader. And if this bootloader fails or is broken, the device is soft bricked. Yes, and that's why the first stage bootloader is not that often exchanged, and that's why it also handles the firmware updates. But as it handles the firmware updates, it cannot update itself. This has to be done after the update from the OS or with the help of UPT or something else. The next, but the most important component is the OPT. This is called Open Portable Trusted Execution Environment. As this enforces some security on the SoC, this also has to handle some hardware configuration jobs that are handled by PSCI and SCMI, but I mentioned this later. Yes, mainly the OPT provides the trusted OS services, which can let them be used by the trusted applications. They use file access, cryptographics, and something else. All of this functionality is mostly implemented with standardized APIs. The organization is called Global Platform, and they are working since 20 years on these standards. And OPT is one of the Ts that implement the T-client API, this bit between OPT and Linux. The internal core API is for trusted applications using OS services, and the cryptographic operations API. So this slide shows the trust zone extension to secure peripherals. This means you see the blue and magenta boxes, and sometimes the box is blue, sometimes the box is magenta, or sometimes the box is mixed. Then this I don't go in detail in this on the slide, but I want to show that there's a trust zones extensions all over the system to partition the devices inside the SoC. This begins by the RAM, das ist the system RAM, the DRAM, partitioned, and yeah, the main, if you, sorry. Yes, while using OPT on your system, it means also that the peripherals which are used by OPT cannot be used by Linux or any other lower privileged applications or OSs. And that's more or less project-specific decision. Do I need the 𝗀 for internal secure storage on a SPI flash, or which IC port is used for the PMIC that has also been secured as so I think we can go to the next slide. The slide was only intended to show that almost every part of the hardware could be separated. But I see the next slide, and here you can see on the left an image. This here we've seen magenta and the blue box, and these are two different OSs or software ecosystems. They run on the same SoC and same CPU and share some other hardware too. But the peripherals shown in the previous slide has to be assigned mostly to one of them, and then this is the master. Yes. Genau, on the left side we see the architecture. This is very similar to something like Linux or any other OS. We have a high privileged OS. It's called OPT core. And then we have a user space. In the user space are running the libraries and applications. And they can use services from the OPT core OS. Genau. And the main goals of OPT is the isolation, to run two independent software ecosystems on the same SoC. It should be very, very small, as it must fit mostly in the on-chip memory, as RAM encryption is a very rare feature today in low-cost SoCs. And last but not least, the last feature was the portability, as it's stated in the name, open, portable, trusted execution environment. On the left side, the picture should show how the boot stages are called the next stage, or how is this handled. Firstly, the ROM code starts after the power on reset, initialize minimal hardware, and loads the first stage bootloader, the FSBL, into the SysRAM. This is the on-chip SRAM. It's about 160 kilobytes, and that's why OPT has to be small too in the first place. But TFA fits easily in this storage, in this memory. The next step if TFA gets started is firstly to init the hardware, the peripherals, secure the peripherals, the RAM partition the device how it's needed for the project or the customer. And after the system is secured, this means the secure world has a watchdog and an IIC port with the PMIC connected and can manage the system resources. On the next step, TFA loads all next step binaries. In this case, this are the U-boot as the second stage bootloader. It gets loaded on a specific address and also verified by TFA for a secure boot, trusted board boot in this case, is it called. And this next stage would then, it's the same stage, but it's another binary in another context. It's the secure context on the SoC, has no access to the non-secure and other side around. Yeah, OPT gets loaded, validated, and afterwards started. Then the boot chain is finished on the secure side. OPT resides in the memory and runs there, provides these services to trusted applications and to Linux. And after this, it jumps to the U-boot and let the non-secure world execute. So the non-secure world starts up with U-boot. The hardware is already initialized. The peripherals are partitioned, the RAM partitioned, and U-boot is aware of this, as OPT gives them this information in the device tree. And then we see a normal boot as on the most other systems, U-boot, loads Linux, device tree, RAM disk, something like this, and jumps over to Linux. Then Linux gets booted and the user space appears and our Linux applications start. So at this point, we have two OSs and more applications on the same SoC running. So the next slide, please. Then we can. Yeah, here another image of the OPT architecture or boot chain. But on this image, it should show the users of the OPT provided services. This could be time service or something we have mentioned before. But on the STM32MP13, we have two system services for Linux and U-boot. They are provided by ST. This is this power state coordination interface. This is related to the management of the secondary cores, system shutdown and reset, on something like this. This is normally directly controlled by Linux, but as Linux doesn't have access to these registers or devices, it has to use the power state coordination interface to tell OPT that OPT should configure or set up the hardware in a secure manner. The next service is the system control and management interface. This is very important as this controls the reset, clock, and regulator controllers. And reset, clock, and power management is very important in case of physical attacks or also attacks like on the x86 Intel platform was disclosed in the last years. They are also on the ARM platform. Yes, both services are provided by ST. And the next, that OPT has also native functionalities. These are provided and for the users, Linux or the other OSs. That's mostly the global platform T API. Here we have hardware accelerated crypto operations, mostly security services like crypto operations or something like this. Yes, the next secure services which are also included in OPT is one very important, is the secure storage service. This can store information on unsecure storage devices. The next one would know trusted user interface. So an application with a GUI can be developed, which has also access to some information this OPT handles or the gatekeeper is, certificates or something like this, and temper monitoring. Okay, exactly. So one example of an OPT runtime service is the secure storage service, and how is a valuable object stored by a trusted application. How does this work? We have the two worlds, secure world on the left side, non-secure world on the right side. The non-secure is Linux, the secure is this with the OPT OS. So the trusted application on the left side, number one, wants to store, let's say, a private key, and then it invokes it uses the internal core API library and invokes a system call to the OPT core. And this application wants to save something in the T, the trusted execution file system. This is not a real file system, it's only a virtual file system. The key on the right bottom should make clear that this information gets encrypted from the TFS driver, and then afterwards the encryption happened, the data is transferred to the unsecure world or non-secure world. This happens by invoking the OPT driver in Linux, which then also invokes another component, the 𝗙supplicant, that's the user space tool. And this tool finally writes the encrypted data to the unsecure storage on the device. And here it's called REFS. That means Rich Execution Environment. Here we have a lot of functionality in comparison to OPT. These are only core functions. Okay, I think I have everything mentioned. Yeah, next slide, please. Another trusted application would be the 𝗶𝗂 number 11 trusted application. This is a API, also known as cryptokey, and this provides cryptographic services like encryption, decryption. This does also OPT. Yes, but OPT offers this functionality only to trusted applications and not to the Linux kernel. Secure generation and verification, and also key generation and storage. These are the topics of the 𝗶𝗂 𝗟𝗶 API. This uses a simple object-based approach. This means everything is an object, and this makes this technology very independent of the hardware. The 𝗶𝗂 number 11 interface is designed for smart cards, hardware security modules, and this mostly means that a human uses this device to secure access at a building or ATM, something like this. Additionally to this, to define a PIN which the user has to put in, we can also define objects as sensitive or unextractable. If an object is defined as unextractable, this information can only put into the HSM, but never can be read out of this device. So I have my key storage. That's my security features. Here, what are the use cases for this IoT device provisioning, entity management, firmware integrity verification, certificate-based authentication, secure communications, everything that has to do with asynchronous cryptography or synchronous cryptography can be supported by this. But it's only it stores keys, key pairs, secrets, but this is the only information it can store. And yes, next slide, please. How is this interface used? The 𝗪𝗂𝗃 API isn't designed like a device or socket or something like this. It's only a header file. This defines function calls. And most 𝗪𝗂𝗃 API implementations implement this as a shared library. This means there's a SO file in Linux as a dynamic linkable object, and the library translates the cryptographic requests into the OPT calls. So this is more or less a proxy between OPT and the 𝗵𝗂 interface. Yes, the application, the custom application can be linked statically or dynamically against the library. Both has pros and cons. Dynamic is sorry. On the right side, you see a picture about common libraries and applications that implement the 𝗶𝗂 API, and this is a very huge. This interface is very old, and therefore that's why this is also widely adopted by the most applications. And yes, the only requirement for the 𝗶𝗂-𝗟𝗶 trusted application is a secure storage service. The secure storage service was mentioned before and is also implemented with trusted applications in OPT. So, and why is the 𝗶𝗂-𝗟𝗶11 not called a service? A service is mostly consisted of more than one trusted applications, and this one is a single trusted application which provides this functionality. But the only dependency is the secure storage service to securely store secrets and keys. Okay. Next slide, please. So with this last mentioned trusted application, we have the platform security services, key management, authentication, secure storage, and cryptographic services, also to the non-secure world, or sometimes called normal world, but non-secure is better. Yes, so finally, Linux in combination with OPT has a lot of functionality that is mainline today and can be used by anyone who want. Hopefully, patches are mainline to OPT and improve this great project more and more over the future. So, I think that was my part. Yes.
Yes, so thanks a lot, Johan. Thanks, Andreas. Thank you. Thanks all of you for listening. Our technical problems. Thanks for also spending a bit more time than we intended to in the beginning. I guess you have now heard a lot about our mainline Linux strategy and how it can help to keep your device secure and up to date. Also, Johan showed a lot about the importance of secure boot and security services such as Trust Zone, TFA, and OPT. And you have probably noticed that as we have been talking a lot about STM32MP13, and also as we are an ST authorized partner, we used some of their graphics and diagrams in here as well. And yeah, so I think for now, you can use the quest section to drop us your questions. And also, of course, you can reach out afterwards and yeah, just let us know if you have any more questions about our products, of course, but also if your projects, and always happy to help and to support you in the best possible way. So please, if you have any questions, just use the question section and then your questions. I think we have one question which refers to the difference between STM32MP13 and STM32MP13. If there is a difference, or especially when it comes to the number of keys, kind of difference you could notice. I think, Johan, we had that topic. Maybe you can just give a very short answer on that.
The main difference related to security features on the STM MP13, I think I only mentioned that, so it was not directly on the slides. The MP13 has a support up to 8 public-private key pairs for secure boot, which everyone can revoke afterwards. So we can maintain a secure device also if some keys got compromised through some customers or employees. This is the main on the secure boot side. Was this also related to some non-security features? The question?
To be honest, I'm not sure, but I think for now that answer is good. Because we have 2 more questions.
Okay.
Yeah. One more question is, if I want to leverage this functionality, for example, with FSL, then I just need to configure the OpenSSL PKCS11 correctly. So will you say that is true?
Exactly. That's is like it should work. And this is also the mentioned or documented way on the OPT side. As this is a mainline trusted application, the documentation is also there. I can share the documentation link if required. But yes, this uses the standard PKCS number 11 interface in Linux or other OSs. And this is only a header file interface. This is very, very simple. This doesn't need any support of the OS.
Great. We have one more question. It says, it would be great to speak about the Yocto configuration to enable secure boot. Is there anything you can add, or I'm not sure, Andreas, if that is something for you? No, you have just.
I know there is secure boot is a general wording in the OPT TFA world. This is called trusted board boot, and it's fully handled by TFA. That's why OPT and the stages afterwards doesn't have to have this function. Doesn't need this functionality as all is handled on the first stage bootloader after the ROM. And OPT TFA is the main lane in the meta IAM layers.
So
Right.
you simply need to add this to your 𝗀 project, and that's all. Or
I would let the wording simply away. I don't know if it's simple to add this or use this, but I think everyone who has set this up on other board with the mainline components should get it working on the STM32MP13 in a short time.
I think I also have to add here that secure boot is always related to a dedicated product, project, and so on. And also what you got from ST is more or less let's call it test system, where you can try something, you can test something with it, but definitely it has always to be adjusted to the project needs. And yeah, here it definitely also makes sense to discuss this in detail. You can do this with us, maybe also with ST or some other companies which are providing support in that area.
Okay, I think as there are for now, and also as we have spent a bit more than we intended, I think that's all for today. Again, please contact us if you have any more questions. Back to us afterward. We're happy to answer everything by email or just set up a short webconf. So please don't hesitate to contact us afterwards. You will also get the presentation afterwards. And yeah, then we hope to see you next time again. And a beautiful afternoon. And yeah, look forward to hearing from you. So thank you very much. See you soon.
Thank you. Bye.
Thank you. Bye bye.